All right. Hello, everybody, and welcome to the 2022 Viking Motorsports Suspension Design Review. So, starting off, the agenda for the meeting is going to be a design overview, talking about what it is that we redesigned and kind of what suspension is, more specifically like the individual components. And then we'll talk about the design methodology, so the considerations that went into those designs, and then we'll present the design itself. It's a collaborative effort between the entire suspension system. And then we'll talk about the validity of these designs. And then we'll go into manufacturing plans of what are the next steps of how do we take this design to something that can be attached to a car. So to start off, there's some suspension terminology that I'll probably use throughout this presentation so that you're all familiar with what these terms are and what they mean. Outboard suspension refers to all components on the wheel side of the suspension. And so that is unsprung mass. So mass not being supported by the spring and damper system in the car. The inboard suspension is all components that are on the chassis side of the suspension. So that includes spring and dampers. The control arms are mechanical linkages between the inboard and outboard suspension. And they are a tube structure in our case. Toe linkages are a flexible control arm. So it's a control arm that changes length to control the direction of the tires. So in our case, because we have a front wheel steering car and a rear wheel drive car, the rear wheel will have fixed toe linkages, so they will not change, but they will be adjustable. And the front toe linkages are attached to the steering shaft, and they will control the steering of the car. The kingpin axis is an axis that runs through the tire, and it's the axis about which the tire turns, and it is affected by a handful of other angles. The Ackerman percentage is a term in steering geometry, and that's the difference in the turn radius between the front and rear tires, or sorry, the left and the right tires between the two front tires that are being steered and bump steered. And that is the change, it's a change in the steering angle due to the suspension arc. So as the suspension travels up and down, because it doesn't travel in a perfectly vertical line, the kingpin axis changes as the tires travel up and down. And that affects how you steer when your suspension is loaded. So some steering geometry. This left diagram is describing this Ackerman principle. So from a top-down view of the car, the radius of the turning arc between the inner tire and the outer tire is different. And so the angle at which the tires are pointing is different, which changes where the slip angle is of your tires. So you're not traveling in a perfectly uniform arc. And that influences where we place the steering points on the outboard suspension. And this image shows this kingpin axis from a front view and also a side view, compared to a perfectly normal line. And so this kingpin inclination angle, the scrub radius, and the caster angle all determine the placement of this kingpin axis. And so when you rotate the tire, it's turning about the upper ball joint and the lower ball joint. And that is where your tire turns about. And so in our suspension design, we use push rod and pull rod suspension, which means they're the inverse of each other. So kinematically, they're identical. They're very similar. So this is a direct model of our rear suspension. So we have a push rod, which connects to the lower control arm. And as the tire moves up, the push rod reacts the force and pushes back down to keep tire contact with the road. And inversely in the front, as the tire moves up, the pull rod, which is attached to the upper control arm, pulls down to keep the tire contact with the ground. And overall, the goal of the suspension is to maintain sufficient tire contact with the road surface under all driving conditions, so that enough friction is generated to prevent slipping. What you don't want is your tires to spin when you want to accelerate. And so this is another image that kind of describes that in more detail and shows some cutaways of the inside of the outboard assembly. So the overview of the design, for the front suspension, we're reusing the same outboard that was designed for the 2021 car. And the redesign efforts have been focused on a new bell crank design to accommodate a new kinematic geometry design. So we're repositioning the control arms to avoid tube interference. And that also means we redesign the control arm ends. So we're tweaking the 2021 suspension. And the rear suspension, we're reusing the outboard and we're reusing the kinematic design as well, designed by Victor, who's in the call. And we're redesigning the control arm ends for manufacturability. So now I'm going to go into the design and we'll check it out. So we have the left side of the car here. Starting from the inboard side, where we have these mounts which mount to the chassis of the car. The bell crank structure, which is here attached to the spring and damper, shown in blue. And it attaches to a pull rod, which attaches to the upper control arm. So when the tire moves up, the pull rod pulls and keeps the tire contact with the ground, and the ground plane can make that visible. So in order to validate this design, I'm going to move it to different positions in bump and droop for the front and for the rear, and turn the front tire using our steering link here to check that we don't have interference between the wheel shell and the rest of any other components. So this outboard suspension is all the same as last year, and we are going to reuse it. One modification we did do was we moved the outboard steering link position from beneath the upright to inside of this pocket to allow more clearance with the wheel shell here. And so hopefully that will
work. It may require some modification of the upright, but nothing that will compromise its structural integrity. So this design is based around a kinematics geometry sketch, which defines one-dimensional lines of the different suspension linkages. And it starts with tire constraints, both front and rear. And the main inputs are track width and the space between the front and rear wheels, track length. So that's decided before you begin to construct the geometry, and you can view different instant centers of the car. So as these lines move through their arc, the point where they intersect is going to be where forces react, and then that induces roll moments about the body of the chassis. So essentially keeping all of our roll moments close to the ground, and eliminating excess forces on the chassis. So yeah, I'll start by moving the suspension in the front, which was our problem area from last year, to its full bump position. So this is the parametric analysis. So this will update as in response to wheel travel. So distance from the center point of the wheel to the ground. So right now it's touching the ground at 50 millimeters input, and our full wheel travel is plus or minus 30 millimeters. The required amount is 25 millimeters by the FSAE requirements, and so we have slightly more than that in our designed wheel travel. So to put it up to a maximum condition, you can see that the linkages update, and this is now in its bump position. So I exit that sketch, and we go back over to the assembly. All right, and so now our tire has been moved up off of the ground. And it is 30 millimeters above that ground plane. So that is our design for full suspension travel. And we do not have any clearance issues with our wheel shell or control arms, which is what we are checking for. We do have some interference with our outboard rod end and our brake rotor. So we will need to reduce the radius of this outer edge. So I will take some notes on another screen and take a screenshot of this to remind us. So we'll check for that same thing does not happen at the top. No, we have clearance at the top, and that's because of this camber angle on the upright. So the top, the upper ball joint is further inboard than the lower ball joint. So we're just generally going to have more clearance at the top than we are at the bottom. Okay, and so now we can try turning our suspension, or sorry, our steering while it's in full bump. So steering positioning. So if we go up to 38 millimeters, that will be a full lock during a left turn because we're looking at the left suspension. 0 would be a full right turn with regards to the left suspension. So now we are at our full turn. Let's check this. All right, so now we are turned about that kingpin axis. So that is the axis between the upper and lower ball joint. And it's determined by all that geometry we talked about earlier. And so we are still getting some clipping with the lower control arm end. But that we have material we still can remove from these parts. So that can be something that we can change, but it's good that we find, that's why we do these design reviews. And we are clearing our wheel shell with millimeters to spare, but a millimeter is a millimeter. So that is okay. Those are point-to-point distance. Come on now. Minimum distance 2 millimeters. That's even better. Great. And we can modify our amount of full steering on track by adding spacers and stoppers to our on our steering rack. And so there might be some interference here with the end of our steering link, but that's kind of to be expected because the rod end isn't modeled. And that's going to be something that we're going to modify the upright in testing to see when it interferes. So that is okay. So that is our full bump, full left turn. So we're going to come back over and put it as if we were in a full right turn. So that's going to be a 0. Invalid solution. Right. So the dimensions in that model are defined by our steering rack and a couple other things. So yeah, that's how we can create this steer. And then there's a distance mate between these 2 points to visualize that in the assembly. So again, we do not have any clipping or interference issues. So we're looking solid there. And let's check our bell crank. We do not have any interference with this nut and this tube. This is going to be a tight fit, but as I said before, a millimeter is a millimeter. So as long as there exists clearance, the components should have no problem interacting. So I've changed the suspension back to pointing forward, and now I'm going to change the wheel input to our droop scenario. So instead of the suspension being pushed up, this is as if you lift the car up and the wheels fall down. So that is at 20 millimeters, 50 minus 30, which is our maximum travel. So now that that's updated, all right, so you can see how the angle of the tire changes, the camber changes as the suspension travel changes. So at this front view, you can see the rear tire, which is still at ride height, versus the front tire, which is in full droop. And so it's characteristics like that that create this bump steer effect, because the tire at the bottom is still going to flatten out when it contacts the road, and it's going to require, it's going to induce a force, which is going to want to steer the car in this case, the left direction. So the tire would want to turn outwards, right, to flatten out its bottom part. So as we're in full droop, we are looking good with clearance. It's still just that lower control arm mount and the brake rotor. We've already noted that. Okay, so now we can move on to steering. So again, we'll go into full lock as if we were in a hard left turn and in full droop simultaneously. So we're checking the maximum conditions of our suspension travel. This is a full left turn and full droop. Nice. And there's clearly no interference with that wheel shell. We're all looking good. Yeah. And let's check full steer in the other direction. This is a full right turn. Yeah, and so last year, having the steering link below the upright, we ran into huge interference problems with our wheel shell here. So hopefully we have to solve this by moving it up and then modifying the upright by removing material in this area as needed. And we'll do that with the full physical assembly and when we're at that stage. All right, excellent. So I'm putting the steering back into its straightforward position, which will be adjustable on track using the rod ends, so we can set our toe adjustment. That's the static angle, away from center, from perfectly center that the front tires or rear tires, for that matter, start at. And for rear tires, we're going to want slight toe in, so that as you accelerate, your tires are trying to push you into a straight line. And for the front tires, we might start with a very slight toe out or very close to perfectly straightforward. And yeah. So now we can start modifying the rear suspension to double check. We didn't have any problems with that last year, but for the sake of a thorough check, we can modify it similarly into droop and bump. The rear suspension is not going to be steered, so we don't need to worry about changing the toe length or toe angle. So let's move it into full bump first, like we did with the front suspension. Wow. Okay, so we have a slight issue just with one component. So it's going to be a mating problem in the rear suspension, but that's something that we can fix. Let's see. Okay, so this part was just modeled with regards to the static suspension. So the front one's rebuilt just fine. So I don't know what the, it's probably the sketch plane or something like that. Let's try moving the suspension into full droop and see what happens. Or yeah. Actually, this is right. We just put it in full bump. So all the parts rebuilt correctly except for this lower control arm, which should be angled slightly up. But as you can see, none of these interfere with each other in bump. So the physical design is not going to have any interference issues, right? Like with respect to the ground plane, the tire is elevated. So the only thing that stayed static was this lower control arm. everything else updated properly, like the outboard ends. And then again, because the geometry is the same in the front and the rear, when we modify this radius and bring it in slightly, then we will overcome that little clipping issue with the brake rotor. So moving the rear suspension into full droop, we'll probably see a similar visual error with the full assembly, hopefully just with the lower control arm. The rest should adjust just fine. And the main interference area that we want to check is with the pull rod and the upper control arm, because this is like the closest interface here on our rear suspension. So a millimeter is a millimeter. That is still clearing. Yeah, 0.41. Half a millimeter is half a millimeter. So those clear. And top update's just fine. And bell crank's looking good. All of this assembly is going to be reused from last year. And we have the physical models of those. So we also have physical validation that the rear suspension is not an issue. The one thing that we do have left to model is the rear toe linkages. So as I said before, those are static connections to the steering link on the outboard. Without those, the rear tires would be free to rotate about the kingpin axis, and the car would be unable to drive at all. Complete, no, it wouldn't work. So we have to create a link that goes for the rear tires, because they don't undergo steering change. We can use the intended mounting point rather than modify both the front and rear suspension. So we can just attach to the original mounting hole location, then just have a tube that attaches to our lower control arm at some fixed position. So the suspension has passed its test of clearing the wheel shell. The one thing that we caught was the lower control arm having a millimeter and a half of interference with the brake rotor. I'm sure even if we didn't catch that, the brake rotor would have fixed it for us. Yeah, so now we can talk about the front suspension geometry that determines these bell crank angles. So in some typical suspensions and most road car suspensions, there's anti-roll bar parts, which is a link that joins the left and right suspension in the front and at the rear, so that as one tire moves up, it pushes the other wheel down, so as to maintain road contact at all times. With such a light vehicle like we're running, 600 pounds or below, having an anti-roll bar is unnecessary if we use a progressive wheel rate. So that's the rate at which the force reacts to vertical wheel travel. So So in this sketch, this follows the point of view. Is it full droop? So these angles and the distance, the moment arm between the pull rod and where the forces reacted here along the spring and damper axis, this moment arm determines how much of the force is reacted by how much compression distance of the spring. And that changes throughout the suspension motion because the immediate distance, like the perpendicular distances between the pull rod and the pivot axis, which is here, this point, and the perpendicular distance between the spring and damper and the same axis changes as this component here, modeled by these three lines, rotates in space. And so mapping that, Victor did a very comprehensive job in 2021 of creating some really amazing design tools that made this process very easy. So for future VMS groups to be able to use these or to recreate them is invaluable. So parametric analysis. So those moment arms are measured here, the perpendicular distance between the spring and the pivot point and the pull rod and the pivot point. And so as the wheel input changes, these distances change respectively in a non-linear fashion. So it's not a, a 1-to-1 ratio or something like that. And so opening up the analysis, this is now moving on from the design portion to more design methodology. So we've kind of gone through the design overview, talked about the redesigned bell crank, and talked about the modifications to the kinematics and the redesigned control arm ends. And now we are talking about the progressive suspension, which eliminates the need for anti-roll bar in such a lightweight car. As the cars do get heavier, the behavior of the suspension is not as nice, according to Dennis Palatov. So, but for our weight class of car, it's not a problem. So, yeah, the wheel force is simply a quarter of weight of the car at ride height, because each tire is assumed to react that force evenly according to the mass balance of the car. And so if we're assuming it's rear heavy, the front tires are taking less load than the rear tires. And so 145 pounds of force can be expected on each tire. And so as the wheel travel increases, the force can be calculated from the force that the spring is exerting can be calculated due to those moment arms, because the initial force is reacted at the tire road interface, and then that's simply translated through those moment arms into the spring. And then once you know how much the spring changes, and you have a spring rate, you can back calculate for what you expect your wheel normal force to be. So that's how this is iterated. So on the first iteration, you guess a wheel normal force, and the spring rate is calculated. And then for the subsequent iterations, you select a fixed spring rate and back calculate what your wheel force is going to be. And so these are some approximations to generate some curvature data on what our spring response rate looks like. And because we don't have any physical validation, and suspension is a very it's a very subjective thing as to what feels good. This year, our goal is to simply create a platform that's testable and adjustable so that we can fine tune it in subsequent years. So we have a baseline curve for our wheel travel. Yeah, that is going to be a reference for once we have a final driving vehicle, parameters that we can change, such as the camber angle of the car, or this with regards to the wheel force, we can change the spring rate, or we can change spring preload to adjust the suspension characteristics. The dampers that we use, the Öhlins TTX 25s, they also have adjustment on the damping response. So in order to reduce the amount of tilt in the car between front and back, we can tune the front and rear suspension offset from each other with regards to their damping response, so that we don't get a uniform oscillation which shakes the car. So we can make that more comfortable for the driver, but that's stuff that we'll figure out in testing. So we have that adjustability built into the suspension system. Yeah, so our spring rate that was calculated from our guesstimated wheel force was like 330 pounds. So if we were to increase, so say if our car ends up weighing 700 pounds, we have a 50-50 weight distribution. That's 350 pounds on the front. So instead of so that would be 175 pounds on each front tire, and so that changes to 397. So due to the availability of these Öhlins springs, I'm simply looking for a spring that's in between 300 and 400 pounds force, because they're not all available. So that kind of takes us into the manufacturing side of the suspension system, where we will talk about the different components, what we need to buy, what we need to make, and plan for manufacturing. I've been talking for a while. Does anybody have any questions or comments, concerns about any of that?
Sounds good to me.
About manufacturing, when do you think those wings for the arrow will be ready for printing?
I'm not sure. I was talking to Tyler today, and we will try to get designs more finalized by the end of this weekend.
Alrighty.
And yeah, that's we might end up manufacturing those using the school's 3D printers, just because we can prototype faster, and we might need to do a couple versions of them before we're ready to do like a final print, say with Xometry or something like that.
Okay. If we do the final Xometry, that's fine.
Yeah, but Yeah, in the suspension, there are not a lot of 3D printed components. We might have some 3D printed jigs to help position things. So I know Jack Watson is currently working on a little 3D printed jig to help position these front bell crank tabs and the damper tab, which is yet to be designed, but it's just two simple pieces of steel which get welded onto the chassis. But to position these tabs and the damper tab relative to each other and relative to the rest of the suspension. Yeah, so we can take a look at suspension manufacturing and update this as we go. So these are all our A-arm ends. And so there was the one design change that we need to just minimize the radius a little bit on the outside of them to avoid that clearance. And I think we could probably shave some material off on this side. So
is that a front all right?
This is the front upper. They could probably all go a little bit smaller if they can, but it's to adjust for this interference right here.
Okay.
And then like this overhang material can probably come in just to reduce weight of the part, but that's not as critical as just slightly reducing that diameter if that's difficult. And then because we are getting parts made out of 1/4-inch steel anyway, is it a large difficulty to change the thickness of these tabs to be 1/4-inch?
No, those should be the same size, or at least that was the intention. I'll double check that the model reflects that.
Okay, so the main body part still needs to be thicker to accommodate that thicker bearing, but these tabs can definitely go thinner than this material just to reduce weight in our unsprung. So they can become this 1/4-inch steel thickness. Yeah.
Cool. Yeah, I could have just heard for sure.
Cool. Awesome. Yep, so that's those inboard A-arm ends. Yes, so these are designed. These are the inboard A-arm ends are these little tab components here. These guys. And so we'll just need like 16 of them and we'll press fit those bearings into them. And they're just going to be made out of that 1/4-inch steel. That's okay. Control arm tubing. That we have ordered. And we settled with 625-inch OD with 0.065-inch wall thickness. And so 0.625 65 equals So we have just slightly under a 1/2 inch outer diameter. Or sorry, inner diameter. And so the length of these inner sections, which stick into the tube, need to be smaller than that inner diameter. 0.049 495. So, and these are parts that we can fillet or chamfer using a bench grinder to get some curvature on those corners. So 0.495, so we'll go like 485 inches. 12.39 millimeters. Just call it 12 millimeters. Is our okay, so with the 12 millimeter inner, we would be shaving off just these 1, 2, 3, 4 corners on a bench grinder. That's real easy. And we still have sufficient contact area inside to weld. So if you made those in millimeters, 12 millimeters is a good size for the width of those like tabs to stick into the AR ments, or you stick into the tubes. So bearing spacers. So we got the
12 millimeter radius.
No, it's a 12 millimeter width. So this dimension here
Okay.
for that inner, let's make that 12 millimeters.
Cool. Sorry to interrupt.
Oh no, you're good. Yeah, so we got the spacers for the bell cranks. Those are done. Bearing spacers, damper rod spacers, those are done. So we have the 2 sides of the bell cranks. And we have a lot of that aluminum stock in the lab. Matt, are these components that you would be interested in machining in the lab?
The bell cranks?
Mm-hmm. Those bell cranks.
Likely we'll do geometry for those.
Okay. Is there a reason you do geometry rather than make them in-house?
Just so we can use the credits.
Okay. Yeah. All right.
Since they expire soon.
Yeah. I gotta use them up. Cool. So. Outboard reduction inserts. Yes, so in the front suspension, part of the modification is we're going from 5/16 bolt hardware to 1/4 inch. So we're going to need to make some very simple reduction inserts that press fit into this hole to reduce the size of that hole. So 7.94. So they're just like a simple part like this, out of steel that we'd press fit into the aluminum upright to reduce the size of that hole. So that's something that we can make in-house on a lathe. The steering linkage at the front, bit on that. We have the tubing has been ordered. We have the weld inserts in the lab, and we have we have the rod ends that screw into those threaded weld inserts. That's all good. Rear toe linkages, we have the materials ordered. We just need to design some very simple mounting plates to attach to the rear lower front control arm. So just some tabs coming off of here to attach this the bottom linkage that is not modeled here. And mount tabs from bell crank, control arms, and dampers. We'll get those water jet by Portland Water Jet, and the jig is being made by Jack Watson, the work done by him. So the thing that we still need to figure out and get done is the steering shaft and this gearbox that is still in progress. And so if anybody in the suspension subsystem has time to assist James with that, we just got to get that done so we can put it on the car when the rest of the suspension system is coming together. So that's looking like the end of this quarter, and definitely needs to be done by the end of spring break at latest. So yeah, those are all of the components that we have in the suspension system getting manufactured or remanufactured this year. Our timing so far is pretty good. We hope to have a rolling chassis with suspension and steering by the end of spring break. And yeah, I look forward to seeing all this come together. It wouldn't have happened without some design tools that were put together last year. And I hope that VMS can continue to use them and iterate on them to create suspension systems in the future. There's a lot of really great resources. Race Car Vehicle Dynamics by Milliken and Milliken is a great resource for understanding where these roll centers are during the suspension travel of a vehicle, and mapping that to real world space to inform your design. The history of suspension really is iterative. People started with wagons with straight axles and thought it was uncomfortable, so they added more components. So it's really an iterative process that needs to be tested because the feeling of the suspension is ultimately what matters. There's a lot of design guidelines, some really big things you should and shouldn't do. But overall, yeah, you can definitely build a suspension for a vehicle. So yeah, thank you for tuning into the design review. I'm going to stop the recording